and right now we can set the stage for the next speaker, who's from Amazon Web Services. He's called Professor Stephen FLAMMIA, who has done very important work in different areas of quantum information, quantum computing, and related topics. And it's a great pleasure to have him here. So, Stephen, if you could turn on your microphone and your video, that would be great.
Yes. So it's a pleasure to be giving this talk. I'm sad that I can't be there in person, but it was very last minute. So I'm going to tell you about a paper that I wrote around this time last year called Averaged Circuit Eigenvalue Sampling. This is about estimating noise processes in quantum computers in a scalable way, very efficiently.
Sorry for a second. Omo, if the microphone in the seminar room could be turned off because there is like a feedback loop. Okay, great. Thanks.
Right. And if you have any questions, feel free to stop me and ask questions in the middle of the talk. It's fine. So this talk is about characterizing noise in quantum systems because we don't have general purpose error-corrected fault-tolerant quantum computers yet. Understanding the noise in them is essential, but it's also intractable just by a parameter counting argument. If you have an n-qubit quantum computer, then describing a general noise process requires 16 to the n, about 16 to the n parameters. So you can't even output the answer. That means that it's pretty fundamental that we have to make structural assumptions about the noise if we want to make learning tractable. And in this talk, I'm going to consider a rough dichotomy of two types of noise, what I'll call coherent noise and incoherent noise. And these aren't really exclusive. They can overlap, but I think it's useful to keep these in mind as two sort of paradigms for how noise behaves. And roughly speaking, coherent noise is noise that can be estimated and calibrated away by tuning your Hamiltonian. At some point, this becomes impractical. So, you know, we tune our 1-qubit gates and our 2-qubit gates, but at some point there will be couplings to the environment, degrees of freedom that we don't have control of. And at some point, we no longer have the ability to correct for coherent rotation errors in our quantum system. And at that point, we're left with noise, which I will call incoherent noise. And I'll be more precise about what I mean by this in a moment. And incoherent noise, I will make synonymous with the term polychannel. If you don't know what a polychannel is, that's fine. I will define it in another slide or so. But why am I focusing on polychannels? It's because detailed knowledge of the poly noise can dramatically, there's a lot of good reasons. So one, it dramatically improves quantum error correction performance. So you can do things like exploit the noise bias in a polychannel. If phase flips are more probable than bit flips, then you can use this information to tailor your code in your decoder. My former student, Pablo Bonilla-Taides, wrote this paper called the XCZX code, which was used in a recent Google experiment. And they needed to use this code in order to demonstrate below threshold, an improvement in the logical failure rate when they scaled their surface code. So these effects are important. We can use tools like dynamical decoupling or polyframe randomization or randomized compiling to take noise sources which are coherent, but which we don't have the ability to correct because maybe it's a coherent many-body interaction and we just don't have enough control to correct for it. We can turn those coherent errors into incoherent errors by using these types of tricks. And this is important because coherent errors can add up constructively and cause more damage as I do deeper circuits and longer computations, but incoherent noise is fundamentally stochastic or probabilistic. It doesn't really add up the same way. Also, quantum error correction seems to make noise incoherent because when you measure a syndrome in an error correcting code, you don't expect to have a superposition of two different syndrome measurements because your classical computer is a large, noisy macroscopic object which is processing these syndrome measurements. You don't expect to have any coherence between those. So quantum error correction makes noise. So the approximation that my noise is incoherent at some stage in the course of an error-corrected computation This becomes a better approximation when you're doing error correction. And lastly, we heard in the last talk about things like zero noise extrapolation, and there are other error mitigation techniques. These techniques work best when the noise that's being mitigated is Pauli noise. So we can combine knowledge of a Pauli channel with error mitigation techniques to try to remove some of this noise via post-processing. So these are all really good reasons to have a detailed understanding of learning Pauli noise channels and describing them efficiently. Okay, so there have been a lot of techniques to try to estimate noise in quantum computers. Most of them have the word benchmarking in the name. The original is what's called randomized benchmarking. Many of you will have heard of randomized benchmarking. It's a way to estimate the average error rates over the Clifford gate set in your quantum computer. It returns basically a single number, which is this average error rate. There are lots of variants that experimentalists use, like interleaved randomized benchmarking as a way to get individual gate error rates, simultaneous randomized benchmarking to learn about correlations between noise sources, between two different types of gates that you're running simultaneously. And then there's a bunch of others. So it became a little industry to sort of come up with these things. In this talk, I'm going to introduce a method that unites most of these, not quite all of them, but most of them, into a common framework. And it will give you strictly more information, and it will use weaker assumptions than the standard theory for randomized benchmarking. And it's basically the simplest thing you could possibly imagine, which is why I really like this result. I hope you like it too. So let me give you some definitions. So what is a Pauli channel? A Pauli channel is just something that acts on a density operator as a convex combination of Pauli noise. So I can just write it in this form. This is the Krauss form for the noise channel E. It's just a probabilistic mixture of Pauli operators acting on your density operator. So P here is a probability distribution, and A indexes one of the 4 to the n Pauli operators modulo phase. So I just said exactly that. Okay. So it's convenient. I'm not going to really use this structure, but I just wanted to highlight it in case there's someone here who knows. This may be interesting if you have a certain background, like maybe some electrical engineering. You can map the Paulis and their multiplication modulo phase can be rewritten in terms of pairs of bits and addition mod 2. So you can think of these Pauli operators and their action as being addition of bit strings mod 2. So whenever I multiply two Paulis, they don't exactly commute. They only commute up to a phase. And if I multiply PA times PB, then I get PB times PA up to this phase. And I designate that phase by this quantity here with brackets, A, B in brackets, where AB is this dot product of the bit strings that I use to describe the Paulis. Okay, I mean, this is just a concise notation. You can also just work this out. But the point is you can do this computation on n qubits in an amount of time that scales linear in n, not in 2 to the n, which is how long it would take if you formed the matrices and multiplied them. Okay, so this is standard material from like chapter 10 in Nielsen and Chuang, for example. Okay. Every Pauli channel has a spectrum as a linear operator. And I will define what I call the Pauli eigenvalues in this way in relation to their Pauli error rates, this probability distribution P. So why are these the eigenvalues of the channel? Well, imagine that I act this channel not on a density operator, but on a Pauli operator. Okay, and let's act the channel on Pauli P sub B. Well, what happens? This is the definition of the channel. And this guy commutes through with this guy or anti-commutes with this guy by picking up this phase. But Pauli operators square to the identity. And so therefore I get, this object here summed over A times PB, which is exactly this object. Okay. So the action of the channel on PB gives me back PB times this eigenvalue. So these are the eigenvalues. This is true for every Pauli channel and for every Pauli eigenvector it's a matrix, but it's still a linear object in a vector space, so it's still a vector. So these are the eigenvalues. So that means that all pallies are diagonal in the same, all pally channels are diagonal in the same basis, namely the pally basis. And these lambdas are their eigenvalues. So all pally noise channels commute is another nice fact. I just said that. The relationship between these, the eigenvalues and the error rates, the pally error rates, this is invertible. And if you've studied a little bit of electrical engineering or signal processing, you might be familiar with the Walsh-Hadamard transform. This is essentially the Walsh-Hadamard transform, which relates the error rates and the eigenvalues. It's not quite, because the matrix ordering is slightly different, but it's essentially the same. And I tell you this because it can help you with some intuition, namely that you should think of the time domain as being like these eigenvalues, and the frequency domain as being like P, the error probabilities. What we want as experimentalists, I'm not an experimentalist, I'm a theorist, but what experimentalists want is to know the error probabilities. Theorists want to know this too. That's like trying to learn the frequency spectrum of a noisy signal or of some signal, but you can only sample that signal in the time domain. So you can see some waveform, and then you want to extract the frequencies. That's exactly what we're going to do. We're going to look at these lambdas in order to extract these P's. Okay, so I hope that intuition helps. Now, I mentioned this idea that I can make the noise incoherent. So for a general noise channel, I can twirl the noise to make it incoherent. What does twirl mean? So if I take a general noise channel phi and I write it in Krauss form, it acts like this on a density operator. So I would just put rho in here in the middle. I can expand each of these matrices in the pally basis, and I get some expansion coefficients. And then if you do the twirling operation, which is you just average over different pally frames, I'll talk about this a little bit more later, then I can define the averaged error rates to be these quantities. So if these things are sort of close to a specific pally, then these things are, it's very close to an error. It's an error channel, which is a pally error channel after it's twirled with specific pally error rates. So this works in real life. This is data from an experiment on a transmon system where they had a coherent error in their transmon. This is for their identity gate. And after they randomized, they were able to eliminate. So these off-diagonal elements that you see here are infidelities, or these are, some errors of some magnitude, 0.064, 0.069. After they do this pally averaging trick, they were able to eliminate these off-diagonal errors. And so what you're seeing, because this thing is diagonal in the pally basis, you can see the labels for the basis here and here. This is diagonal in the pally basis, so this noise channel is a pally channel. And these are the pally error rates. And moreover, this transformation has preserved the diagonal entries of this matrix. You can see that within statistical error bars, each of these diagonal entries is the same in the unrandomized and randomized cases. So what this means is, because the fidelity of a noise channel to the identity is the trace of this matrix divided by 4 in this case, the noise fidelity is actually preserved under this transformation. So we've eliminated the coherent errors, and we've preserved the average error rate of this channel. And that was data from a real experiment. So the point is, this works in real life. Okay, so many of you will know what the Clifford group is. In case you don't, it's just the group on n qubits generated by single qubit Hadamard gates, phase gates, and controlled NOT gates. And the important thing about the Clifford group is that if I act on a pally, which I denote in this way, G acting on P, which just is my shorthand for this conjugation action, okay, then I get back a pally up to some ±1 sign, okay? The plus and minus 1 signs are important, but they're really, if I were to track them throughout this talk, it would be distracting and inconvenient. So I'm going to completely ignore these plus or minus signs for the rest of the talk. Okay, so now I want to tell you about this average circuit eigenvalue sampling with the really cool acronym ACEs. So consider an n-qubit system with a bunch of Clifford gates GK, okay? And each gate, I'm going to allow every gate in my noisy quantum computer to have its own Pauli error channel. And the noisy version, I'm going to put a little tilde on top. And then I'm going to have the ideal version, GK. And I'm going to decompose the noisy guy into a Pauli channel times the ideal Clifford. Okay. And I can always do this because I can just define the Pauli noise to be the pullback. I just multiply by GK dagger on the left, and I'm left with a definition of my Pauli noise channel. So this is a model that I'm going to use to define this noise. If it doesn't hold, then I'm going to have to do some Pauli averaging in order to force it to hold. I'm also going to allow state preparation and measurement, or SPAM, errors, and I'm going to assume that only Pauli noise can affect the state preparation and measurement errors. Our goal is to learn all of these noise channels EK for every Clifford gate up to some noise precision epsilon. And let me go back for a sec. I'm going to assume, furthermore, that if I do the same gate twice in the same circuit, that it has the same noise model. So my noise is time stationary in this sense. If I allowed for arbitrary time-dependent noise, then it becomes more complicated. I would have to do a time series analysis. I'm going to assume that everything is time stationary. This is sort of like the DC offset of your noise, if you will. So ACES achieves this. It learns all of these Pauli channels to some precision epsilon, and it does it extremely efficiently. It uses a small number of quantum circuits, like maybe 20. You have to repeat these circuits some number of times. So I have to sample from the output of these circuits, but I only have to sample a polynomial number of times. And the classical resources that I need to pre-process and post-process these experiments is also efficient. It's polynomial. So what if your noise isn't actually Pauli? Then this is this Pauli twirling trick. This is a figure by this paper by Wallman and Emerson called randomized compiling. The basic idea is I just take a circuit and I insert random Pauli operators into the circuit, and I run the circuit multiple times in different random Pauli frames with the constraint that the overall unitary operation is the same for each Pauli randomization. And you can do this by splitting these random Paulis and like recompiling the circuit in different ways. So it's like choosing different frames at each time step in the circuit in which to apply the noise. This is basically, if you're an experimentalist, it's like running a pi pulse, a randomly chosen pi pulse in every time step between each circuit, but it's a little bit more efficient than that. So what we're going to do is for every circuit that we want to run, we're actually going to sample from this ensemble of circuits. And you only need like a dozen or so samples from the ensemble in order for it to converge rapidly to incoherent noise. That's from experiments by Irfan Siddiqui's group. Let me move ahead. So because we're going to employ this technique to randomize the noise to get rid of any coherences, we're just going to assume now that the model is correct, that all of this noise is exactly a Pauli channel. So now in a long circuit where the ideal gates are G1, G2, all the way up to GT, the noisy version is the noisy channel followed by G1, then the noisy channel associated to gate 2, followed by G2, and so on. Let's suppose for a moment that this circuit, the total circuit, is actually the identity. So the product of all of these gates in the ideal case is just the identity. Okay. Not a very interesting circuit, but what can we say about it? Well, what are the eigenvalues of that noisy channel? I claim that this channel is in fact a Pauli channel. Why? Well, it's because if I send a Pauli through, the only thing that can happen is that this Pauli channel acts on a Pauli operator and picks up an eigenvalue, and then this gate permutes that Pauli to a new Pauli because that's the definition of a Clifford operator. And then that just repeats. And by the time I'm done, that permutation has to go back and bring my Pauli back to itself, possibly up to a phase, but like I said, we're going to ignore those phases. And at the end of that, I will have picked up some eigenvalue and I'm back to my original Pauli. So therefore, that's true for all Paulis. Therefore, whatever that eigenvalue is, the Pali is back to itself times a scalar. That's the definition of an eigenvalue. So this is a Pali channel. Okay. So now, what's the relationship between the eigenvalue of this circuit and the individual eigenvalues of each of the individual noise channels? Well, inductively, what we can do is we can say if the first gate takes Pali PA1 and maps it to PA2, I just define PA2 this way. Inductively, I can define the next Pali and so on. So as the Palis propagate through the circuit, they permute to new Palis and so on. Each time I do this, I pick up an eigenvalue. I pick up the eigenvalue for the gate 1 acting on Pali A1, the gate 2 acting on Pali A2, and so on until I get the eigenvalue T acting on AT. So this eigenvalue is the product of all the individual eigenvalues, okay? After twisting by these Palis and by these individual gates. If C is not the identity, something very similar holds, except it's the notion, I need the notion of a generalized eigenvalue and a generalized eigenvector. A matrix, if you have a matrix A, then lambda is a generalized eigenvalue with respect to fixed matrix B, whenever A times V gives you lambda V, B times V for a fixed matrix B. So what happens if C is not the identity? So yeah, that's a generalized eigenvalue and eigenvector is where you twist by some matrix B. So now what happens is it's a good exercise to try to work through this. C tilde acting on P gives me back the same eigenvalue, but with the ideal circuit acting on P. Okay. And you can see if the ideal circuit were the identity, this reverts back to the previous case where it's just a Pali channel. So now it's a Pali channel where these eigenvalues are the generalized eigenvalues, but this product relationship still holds. Okay, so let me just recap what we've achieved. So now if I have the ability through circuit averaging, Pali frame randomization or randomized compiling to construct Pali channels out of all the noisy gate elements in my circuit. I can compose these to get a new Pali channel with an eigenvalue at the output, which is a function of all the individual eigenvalues of all the individual noise processes that have gone into that circuit. And moreover, I want to just stress I can calculate all of this efficiently classically because of properties of the Clifford group. So now I'd love to have access to this eigenvalue associated to the circuit, capital lambda. And I need to be able to do this in an experiment. So how would we do this? I can't prepare a Pali P, but what I can do is prepare a state that's an eigenstate of the Pali P, either the plus or the minus eigenvalue state. And if I do that, and then I difference those two state preparations, then I can get access to that eigenvalue experimentally. So basically, if I prepare a plus eigenstate and I sample the output average by measuring this Pali expected value, and I prepare the minus state and I average that Pali expected value, the difference of those two counts from my experiments is exactly this eigenvalue. Okay, so therefore, just by sampling from some input states that are easy to prepare, so states of this form, so the state up or down, or the state plus or minus, and sending them through the channel and measuring at the output, these are like the exact kinds of experiments that experimentalists can do. I can access these eigenvalues. Okay, and this is easy to do as long as the Palis that I'm measuring at the output aren't like n-body Palis. As long as they're like 1, 2, 3, 4 qubit Palis, this is tractable. Much more than that, and the signal starts to degrade. Okay, so now we have all the pieces to put together. And I started, I'm at 25 minutes now, so I have 5 minutes, is that right? Each pair, for each circuit that I choose and each Pali input, P. So when I say a Pali input, I really am meaning that I send the eigenstates of P in, up or down eigenstates. So for every pair of circuit and input, I'm going to define a label mu, which defines that experiment. The Pali error rates of a gate G define a bunch of model parameters. So for every Pali error rate and every individual gate that I have in the system, I get a bunch of model parameters associated to those Palis and those gates. I'm going to bundle them into a composite index called nu. I just want to emphasize correlations between gates can be modeled this way too. The gate doesn't just have to be a Hadamard gate. For example, I might be interested in a gate called H1 times H2. This is like simultaneous randomized benchmarking where I do H1 and I do H2. But if I do H1 times H2, I have different noise because of crosstalk that happens between these gates. So I can add this too. Anything that I want to add here is a model that I can add into this class of model parameters nu. Now, intuitively, once I have more experiments than I have model parameters, or more measured experimental parameters than I have, input model parameters, I should be able to identify those model parameters intuitively. But how to find it? So we'll see that this is correct. This intuition is correct, essentially correct. So this is the protocol. We remember from slide 4 or whatever, this relationship between the Pali eigenvalues and the Pali error rates that we're trying to learn. I'm going to transform variables. So as long as my noise isn't too far from the identity, which it shouldn't be if I'm building a quantum computer, then these eigenvalues are all positive. This is easy to prove. I'm not going to prove it. If this is a positive number, then I can write it as e to the minus x for some x, which is also positive. Okay. So now I have new variables x. The output of the experiments allows me to sample the eigenvalue of the circuit. And this will also be positive as long as my circuit isn't so deep that I've destroyed all the signal from my experiment. So I'm assuming now that these eigenvalues are also positive. In these new coordinates, because capital lambda was a product of little lambdas, these x's in exponential parameterization, they compose linearly, right? The x's just add up, which is really convenient. So that means I can define the log of this lambda to be some new parameter that I estimate. I just take the log of my empirical estimate, and I get b. I'm defining b this way. B is now linearly related to X, where the matrix that relates the two is determined by the specific circuit that I have and the specific noise model that I have. In order to create an estimate for all the model parameters, I just have to solve AX equals B. So that's it. There's no machine learning, there's no neural networks, there's nothing crazy that you have to do. You just have to you solve the least squares problem. You just solve AX equals B. As long as the rank of this matrix A is larger, is equal to the number of model parameters that you have in your model, then there's a least squares solution to AX equals B. You just solve it. And then these steps can be, once I know an estimate for X, I take the log. And as I said, this thing is an invertible transformation. So you can back up from these steps to extract the Pali error rates P. And these are my last couple slides. I'll be very quick. This is really scalable. So I did some numerical simulations on my laptop for 100 qubits, where I sampled 20, I think it was like 19 circuits, maybe 20 Clifford circuits of varying depths. And I sampled each of those circuits 10 to the 4 times, 10 to the 5 times, or 10 to the 6 times. These are achievable numbers of samples. If you're in, for example, a superconducting architecture where you have timescales, some gates are, these are nanosecond gates oftentimes, but, even with relatively slow measurements and things like this, you can definitely do 1 million measurements in a second. Ions, it's a little harder. They tend to have slower gates, but so every gate here in these numerics has independent noise on all the Clifford gates. The model that this defines gives you about 900 different gates with 5,000 parameters in the model. This will be a huge model. There's no way you could learn this by doing 5,000 randomized benchmarking experiments. I mean, you would graduate from your PhD, hopefully well before then, if you're trying to make all those measurements. Right, and like I said, it only requires about 20 random circuits. So this is a very small amount of experimental effort. And you can see here, this is a more, so there's two things. One, the circuit eigenvalue estimates, this is in percentage, converge very quickly to sort of Gaussian style statistics with very small fluctuations. So with about 10 to the 6 measurements, I get 1/3%, which is roughly the 1 over the square root of this number. So that means that I'm converging pretty quickly to the right answer and Gaussian statistics for that. And when I invert these estimates for the circuit level eigenvalues, I can find that the total variation distance, or the one norm distance, or the diamond distance of the noise channel, if you will, converges very quickly for all of these gates. So this is a histogram of the noise on all 900 of the gates. And you can see with 10 to the 4 samples, the total variation distance is pretty much always below 1%. The total variation distance is less than, 0.2% or maybe a little less once I have 10 to the 6 samples for basically all the parameters. There's a couple outliers if we zoom in close, but there's always going to be outliers with any noise process. So we expect, just briefly, I forgot I had this slide, the assumptions that, to recap the assumptions that go into this, we've assumed that this Pauli twirling process is exact, that the eigenvalues aren't ever too small, the circuit eigenvalues. Otherwise, when you take a log, you could distort your estimates. This is easy to satisfy in modern quantum computing architectures. And we're assuming in the numerics that the model is correct. If there's a model violation, you can't blame the theorist. If you put in a model and then it doesn't fit, that because the model is wrong, don't blame me for deriving this framework. You should be using a different model. The exactness of the Pauli twirl can be relaxed, and the sample complexity is polynomial. I'll just say that. And this is my last slide. Some future directions. You can turn this into an online streaming algorithm. So as the data come in, you can update your answers. So you can use this to do dynamical error tracking with explicit error ellipses and fast rank 1 updates and order 1 memory requirements. So I have a little visualization of the error ellipse converging to the true answer. So the true answer is this blue dot here in the middle. And this is the exact covariance matrix of the estimate as it slowly converges as I increase the number of samples. So this is work in progress. There's some work to be done to optimize the collection of the data. I have a somewhat related paper that I wrote with Robert Huang and John Preskill about learning more general noise beyond Clifford circuits, but it's kind of beyond the scope of this talk, but you can read about it here on this archive paper. And of course, it would be great if people would use this in experiments. So thank you very much for your attention, and I'll take any questions now.
Oh, thank you very much. It's a great talk. In the last slide, would you mind showing the last slide?
Sure.
Exactly. Is it possible to get stuck in a metastable state, namely having this picture like the spin glass? You're trying to find the solution, no? Is this like conjugate gradient relaxation where there is only one minimum? So you iterate and then this yellow blob zooms into the right answer, or you could get stuck in a metastable state somewhere else, like people who do like spin glass problem or protein folding, they're often getting stuck in some other solution. They think it's a solution, but they're stuck. So how do you know you're going to the right solution and not some metastable state?
Yeah, so that's a good question. So let's suppose for the minute that the model that you have is correct. I mean, if you say every gate has independent errors, but you actually have crosstalk errors between 2 gates, then you're going to converge to something which manifestly has an error, and I can't help you with that. You needed to use a better model. But let's suppose for a minute that your model is, and it should decay gracefully. Like if your crosstalk is weak, your model error, your total error will be small. But let's suppose for a minute that the model is correct. Then the only errors left over in the system are statistical errors that come from sampling noise, or shot noise. And because all you're doing is solving AX equals B, there's not going to be, I don't think you're going to get stuck in a local minimum if you solve it in this sort of obvious way, where you just you take the pseudo inverse of the matrix A. Because basically, let me write on this slide for a second to answer your question. You know, your noise looks like this. You know the matrix A exactly. You're trying to find X, and you're given B plus some noise epsilon. The fluctuations in epsilon are decreasing like this, right? If you sample more and more, that's getting smaller and smaller, and then all you need to do is solve AX equals B. So as long as this matrix is sort of well conditioned, so if the ratio of the largest to the smallest singular value of this matrix is not huge, then that inversion is going to be smooth and you'll never have a problem.
Great, thanks very much. Another question, you're saying the randomization of the circuits is done to remove coherences. The confusion I have is the following. This is an example when people do like astrophotography. You take pictures of planets, galaxies. They always have noise. There is like blurred and fuzzy. So people do stacking. You take a whole bunch of photos and you make an average. So the average removes the noise because then each pixel has a random fluctuation. So therefore the average removes the incoherent part and you get the great photo of, let's say, Jupiter. But so the puzzle is, in your circuit, your randomization is removing the coherences. I thought you want to remove the incoherences because these are the random noise, is like in the picture of Jupiter. You want to remove the fluctuations of the pixels. So that's why intuitively I was thinking, why is he trying to remove the coherences? I thought you're trying to remove the incoherent part.
That's a great question. So I think, you always, experimentalists spend the majority of their time calibrating their device to not have any unwanted coherent errors, right? A gate is a coherent thing. A perfect pi/2 gate is great. If you have it in practice, you tend to have a little bit of coherent over rotation or under rotation. At some point, you have to give up on calibrating. Maybe you're coherently rotating to some two-level system, like in a transmon system. Right? Maybe you have some coupling to some TLS, two-level system. That's bad. And what you want is to avoid having that coherent error add up constructively, right? Because if I apply the same gate a few times and I have the same coherence, that can add up faster than a randomized error. And it's true, randomized errors are in some ways worse because, but also, the philosophy here is you've given up on trying to find ways to improve your calibration. At some point, you always have to give up.
I see.
The reason you want incoherent errors at that point is because quantum error correction is tailored to deal exactly with incoherent errors. Error mitigation and zero noise extrapolation are tailored best when the noise is incoherent. So we want to sort of put the noise into that, we want to make the noise of that form in order to maximize the ability of those other tools to work because we've given up on using our coherences. Does that make sense?
Yeah. That's a great answer. Okay, thanks for the clarification. So I'm looking here at the chat. I don't see any questions on the chat. It is your last opportunity before going to the last speaker here. Omololu, you have a question?
Oliver has a question here.
Okay, go ahead.
So as the experimentalist in the room that's always going to misuse everything you give me, do I get some warning if my model's wrong, at least?
Yeah, probably. Let me think. I think one of the things that you would probably do is you would start with the simplest possible model, and then you would do a check by adding a couple model parameters to see how much the fit improves. The fit is always going to improve when you add parameters, but does it improve usefully or are you overfitting? And there are statistical tests that you can do to test for this. So, maybe you're worried about a crosstalk error between some gates. You can measure that, and then you can use tools. There are these things called a Kaiki information criterion, or there are tools like what's it called? Regularization, like L1 regularization, to try to find the correct, so-called correct number of model parameters. So you can like over parameterize your model, and then instead of solving AX equals B in the obvious way, you can solve it in a way where you've got a bunch of parameters, more parameters than you have experiments. But you solve it in a way that zeroes out the ones that have the least influence or the least effect. So if a parameter is not observable within the statistics of what you've measured, the estimator itself, using tools like L1 regularization or lasso, you may have heard of, will kind of tend to zero those things out, but still give you a relatively unbiased estimate. Unbiased asymptotically, and it's consistent in the sense that asymptotically these estimates are consistent. They converge to zero bias. And you might want to do something like that. I didn't really say how to solve AX equals B, right? Somebody's probably written a book called AX equals B, where, machine learning is kind of 2.0 of exactly that, right? So I think you would want to think carefully about what model parameters you put in, add the ones that you think are needed, maybe add more than what you think is needed, and then use some tools to try to prune the ones that you didn't actually need, that you were just paranoid about. That would, if I were advising you on your experiment, that's what I would do. To be more direct, I'm not exactly sure that it gives a specific signal when you have a model violation. But what I just described is how I would protect against that.
Given that answer, if I just took over complete data and checked chi-squared when I'm done, would I be pretty safe?
I'm not sure. I don't know how reliable a chi-squared statistic is. I don't know. Like these are sort of large scale models, and I haven't thought hard enough about the statistics of it. I would want to do a bunch of numerical simulations before I I don't know. I'm hedging because I'm a theorist, so I don't want to give you bad advice. My advice would be do some numerics. The numerics is super easy to do, is the nice thing here. So it doesn't cost you a lot. You're not doing hard simulations of time-dependent Schrodinger equations or anything. You just do a little bit of sampling, and you should be able to check whether your statistics are converging or not. I think that's probably the best advice.
Thank you.
Thank you very much.